Claisen condensation and Dieckmann condensation. These two reactions we are going to discuss in this video. So actually, Claisen condensation, if the reaction taking place between two molecules, then it is called Claisen condensation. And if the reaction taking place within a molecule, intramolecular reaction, within a molecule, if there are two steric group present, then we call it as a Dieckmann condensation. So actually, this is a Claisen condensation. So what is Claisen condensation? Is a reaction of esters. So we need ester for the Claisen condensation, where at least one ester, one molecule of the ester must have alpha hydrogen. Then what happens? These esters are treated with strong base, and we get always beta-keto ester. Means at beta position there is a carbonyl group. Because of that we call it as a beta-keto ester, and this is called Claisen condensation. So what happens here in this reaction? There is always formation of carbon-carbon single bond, and one carbon-oxygen bond is broken. So this is all about Claisen condensation in general. So to understand this reaction, I have considered here one example. I have taken methyl acetate. So I need two molecules of methyl acetate, or you can take two different ester molecules. If you are using two different ester molecules, we call it as a cross Claisen condensation. And if we are using one molecule where two esteric group present, then we call it as a Dieckmann condensation. So this is the difference between Claisen condensation, cross Claisen condensation, and Dieckmann condensation. Now take methyl acetate or ethyl acetate, it doesn't matter. Now it is having alpha hydrogen. So this alpha hydrogen means next to the carbonyl carbon is alpha carbon, where hydrogen is present is called alpha hydrogen. This hydrogen is acidic hydrogen. So you take another molecule, you write another molecule here, and from another molecule you have to remove this portion. Means what is here? Whatever is attached to the oxygen, that you have to remove, along with alpha hydrogen from first molecule. That hydrogen will go and join here to get methanol. So this methanol is formed, and you have to form a bond between this carbon and this carbonyl carbon. So there is a formation of this bond. You can check here this bond. What is alpha carbon of one molecule and carbonyl carbon of another molecule. So we get what? So if you consider this is a esteric portion, ester part, ester functional group, then the next to this is alpha carbon and beta carbon having carbonyl group. So because of this is called beta-keto ester. So you are getting beta-keto ester. This is the product, and you are going to break one CO bond and forming one CC bond. So we get here methanol as a side product. If you are using sodium ethoxide, you will get ethanol, or along with that you will get different. So it is depend upon whatever base you are using and whatever ester you are using. So you just must be watchful towards the final product. So you are always getting beta-keto ester. So this is general scheme which I have described here, I have explained here by considering one molecule of ester. Now we are going to somehow complicated part of this reaction is the mechanism of this reaction. Which base we are using? We are using sodium methoxide. So this sodium methoxide is like this, which undergoes this kind of ionization. So this is a methoxide ion, which is a base, and this is a sodium ion. Now this base is in action. So we have to take first molecule of our ester and remove this alpha hydrogen. One alpha hydrogen you remove outside. So that is abstracted by this base. It is just acid base reaction. This is acting as a carbon acid. So this is a carbon acid. So acid provides proton, which is alpha proton, to this base. Now for that purpose this pair is used to form a bond between this oxygen and hydrogen. What will happen with this bond? This bond will move as a pair on this carbon, on this alpha carbon. Now this carbon showing that pair, you can find out the formal charge. There are 5 electrons on this carbon, means 1 electron extra, and because of that this negative charge is developed. So you can write here negative charge. But this is carbanion, and carbanion is unstable because of this negative charge. But you can draw a resonance by just shifting this pair in between carbonyl carbon and this carbon to form a double bond, and this bond will move on this oxygen. Once you move that bond on oxygen as a lone pair, this oxygen now having 7 electron. So because of that, negative charge is developed, formal charge is negative. As if this negative charge is moved or delocalized from this carbon to this oxygen, from this carbon to this oxygen. So the negative charge, because of this is unstable, is divided in between these two atoms. So actual negative charge shared by these two atoms is half, which is not complete. So the intensity of negative charge is decreased, and because of that, this is more stable and stabilized because of resonance. And you can put that sodium outside this this bracket. So this is a formation of carbanion. You can say carbanion, or you can say this is a nucleophile. So nucleophile is generated in this step, in this first step. So the first step is formation of nucleophile. The second step, once that nucleophile is generated, which I'll write here, this nucleophile I have taken from step number 1. Now this nucleophile is in search of second molecule of ester. So this second molecule of ester is taken here. Now see, it's very simple. Just what we have seen in acyl nucleophilic substitution reaction, the same mechanism is you can observe here. Now see, this nucleophile having lone pair, it will go here at the carbonyl carbon. Why? Because of this positive charge. This is a polar region of this molecule where positive charge is on carbonyl carbon. So once this is approaching to this will provide a pair to form bond with this carbon, but we cannot have 5 bonds on this carbon, so we have to open one bond on this oxygen as a lone pair. So that is done here. So I have joined here this carbon here only by using this bond. You just see here by using this bond, and this pi bond is moved on this pi bond is moved on this oxygen as a lone pair. Now you can count number of electrons. Now 4 electrons there, so the negative charge is vanished. But here on this oxygen there are 7 electrons. We need 6 electrons, 1 electron extra. Because of that, negative charge is developed. So this is an intermediate compound form which is having tetrahedral geometry here at this carbon. You can see. So that is sp2 hybridized carbon is converted to sp3 hybridized carbon. Now very soon this pi bond is formed. So you have to shift this lone pair as a pi bond quickly. But this time, which bond will break? If this bond is broken, you will not get the final product. That if you are getting final product, that means we have to break this bond. Which bond? You have to break this bond, carbon oxygen bond. So you have to remove this carbon oxygen bond. This bond will move on the oxygen as a lone pair. So this is that bond as a lone pair, and if you see here there are 6 electrons. But once this pair is shifted on this oxygen, it is having 7 electrons. So because of that, negative charge is developed. And if you do that, you can see here a reaction taking place here. I just move this CH3 toward this side, toward the vacant side. So this CH3 is coming here, and this is newly generated pi bond which is generated from this lone pair, and rest of the molecule I kept here as it is. So this base is generated. This base is generated. In next step, this base may remove this alpha hydrogen, because there are still 2 alpha hydrogen and it is more acidic as compared to this one, because it is now sandwiched between 2 electron withdrawing groups. So it is more acidic. So this very soon this will remove this and form carbanion, and that will undergo resonance. So to stop this reaction or to quench this, we have to add HCl. So once HCl is added, this is removed from the reaction mixture as a methanol, which is used as a solvent in this reaction, and this Cl might combine with Na to form NaCl. So in this way we get here condensation product, and this is called actually beta-keto ester. So ester is converted to the beta-keto ester where carbonyl group is introduced. Discuss Dieckmann condensation, which is actually a Claisen condensation, but Claisen condensation taking place within a molecule. If there are two esteric groups, if you observe this molecule which I have taken here, there are two esteric groups. First is here and second one is here. So two esteric group present in the molecule. In between, having how many carbons? Two esteric groups are separated by 1, 2, 3, 4, 5 carbons. So these are 5 carbons. So I'm trying to make it more simple. You take such example where two esteric groups are separated by 1, 2, 3, 4, 5 carbons. Or you can reduce one carbon, two esteric group separated by 4 carbons, either 5 or 4. Is it clear? Now, when this is treated with a base, which is a strong base, and this is acting as a solvent, methanol. You can even change, you can take sodium methoxide and ethanol, but I have taken sodium methoxide and methanol combination. Now, after that, once this molecule is written, you just have to identify alpha carbon. So either alpha carbon here or alpha carbon here. So this alpha carbon you have to identify. So obviously, the reaction taking place where this is going to join to your carbonyl carbon. So when you remove one hydrogen here, this is going to form bond with this carbonyl carbon intramolecularly, and you have to remove this. You have to remove this. You have to remove this OCS3. So you will get methanol. And if you do that, what you have to do? You have to form bond with this carbon. And at this second carbon, so for the to simplify this, you just provide numbers either from this end or from this end. So everything is happening at carbon number 2 and carbon number 7. So you have to join carbon number 2 and carbon number 7. How many carbons there? 1, 2, 3, 4, 5 and 6. So hexagon. So first of all, you form hexagon like this. And you know, at carbon number 7, there is a carbonyl group. This is carbon number 7. Or I can write, this is carbon number 1, 2, 3, 4, 5. I forgot. So I'll keep this numbering. This is 1, 2, 3, 4, 5, 6 and 7. So the bond is formed between 2 and 7. Bond is formed between 2 and 7. And you just count 1, 2, 3, 4, 5, 6 carbon. So form hexagon. At 7 carbon you write carbonyl group. And at this carbon, at second carbon you write that esteric group, COCS3. COOCS3. This group is written there. So you will get the product. If there are 4 carbons in between, so the 6 carbon will be having carbonyl group. So there will be then 1, 2, 3, 4 and 5 carbons. So you just draw a pentagon, and at 5th carbon, at 6th carbon in fact, you have to write carbonyl group. So in this way, by using this Dieckmann condensation, you can prepare 5-membered ring or 6-membered ring. You can practice by considering another example where 1 carbon atom less at your home in your book. So you can prepare 6-membered ring or 5-membered ring in Dieckmann condensation. That's it. Now I'm moving toward the mechanism of this reaction. To simplify, to make it more simple, I'm just considering, instead of CH2, I'm considering this skeletal form, this line form. So as I'm going to prepare 6-membered ring, I'll write to mold this molecule. I'll write to move this molecule in a hexagonal form, nearly hexagonal form. So now see, this is 7th carbon. I started here, and then I wrote all structure in lines only. This is our carbon number 2, where 2 hydrogens present. And what happens? This methoxide is going to remove 1 hydrogen from alpha. So if 1 hydrogen is removed, obviously that pair will form here. I'm not writing here, it's a resonance. You can write otherwise a resonating structure by just shifting here and opening this bond. So you can do it because there is no space, and if I draw that resonating structure, that will occupy more more space on the board, and that doesn't look good, or that will be a hodgepodge, or that will be very complicated, and probably you may not watch this video if you see that kind of complicated structures here. Now this is very close. This is very close means you have to form bond between 2 and 7. This is carbon number 7. So this pair is moving in between this one, and this bond is moving here on this oxygen as a lone pair. So initially you show that two lone pairs. After that, one bond, this bond is moving on this oxygen, so this lone pair is formed. Very soon I have just produced this bond. This bond is formed, right? And I open this bond on this oxygen, just like Claisen condensation. Now if this bond is regenerated, this double bond will try to form it again, but this time you have to break this bond where the oxygen is attached. So if you remove that, you will get here OCS3 minus. So this OCS3 minus is removed, and actually this bond is formed, and this bond is formed. So in this way you get this beta-keto ester. This is again beta, this is alpha, and this is beta. So at beta position there is carbonyl group, but the reaction, whole reaction taking place within same molecule, and that's why another name is given, that is Dieckmann condensation. So in this way you can have this mechanism, and we have learned Claisen condensation and Dieckmann condensation. Even you can try by considering another different two molecules that will be called as cross Claisen condensation. You can try on your book, I mean on the paper, and if you are having any problem you can ask me, so I'll try to explain it once again. Thank you.